Okay, so in this segment, we're going to finish the proof of the correctness of Shor's algorithm for this more relaxed period finding problem. Okay, so this segment is optional. It's a bit technical, but if you want to see all the details of the proof of correctness of Shor's algorithm, then of course you're welcome to watch it. Okay, so again, what is left for us to prove? So what we need to prove is the following. So we had this state GT, and in the previous segment, we argued that if after we applied the Fourier transform to GT and we measured, we saw an index B, which was good in the sense that there was a K such that the period S was relatively prime to K, and B times S was fairly close to K times N, then we were done. So then from this B, we could compute S, okay? So to show that Shor's algorithm worked, we needed to show that we would, when we measured the Fourier transform of GT, that we would find such a good B with, a decent probability. And what I claimed there was the following lemma, that on measuring the Fourier transform of GT, we see a good B with probability at least 1 over 100 log S. Okay, so this is the lemma that we're going to prove in this segment. Okay, so the first thing that we're going to do is just to lower bound the number of good B. Okay, so this has, nothing to do with the quantum algorithm or measuring. We just count the number of good B. And the kind of key idea for this is instead of counting B's, we actually want to count K's, okay? And the claim is that the number of good B is at least the number of integers K, which are relatively prime to S, okay? So let's see why that's the case. So there's two conditions that we have to satisfy to be good. So the first is that K has to be relatively prime to S. So obviously such a K satisfies that condition. And the second condition was the closeness condition, right? So B times S had to be relatively close to K times N. So let's think about that condition now. And basically the claim is that for every K, there is an associated, every K which is relatively prime to S, there is an associated B which is good. Now why is that? Well, let's just write K times N as A times S plus C, where C is between 0 and S minus 1, right? I mean, any number we can write in this fashion. Okay, now let's think about C, right? If C is at most S over 2, then that means that A is good, right? Because then K times N minus A times S, it will be less than S over 2, and K is relatively prime to S, okay? Now, if C is greater than S over 2, then that means that A plus 1 is good, right? Because then A plus 1 times S minus something at most S over 2 would be equal to K times N, okay? So basically for every K, which is relatively prime to S, there is an associated good number, okay? Also, the good elements that we're obtaining this way are distinct for different Ks, so that gives the claim, okay? The number of good B is at least the number of K, which are relatively prime to S. Okay, so now let's just lower bound the number of Ks which are relatively prime to S. and this is a well-known fact, number theoretic fact. So there's actually a function called the Euler-Toshin function, which counts the number of integers between 1 and z, which are relatively prime to a number z. Okay, and it's known that this that phi of z is at least z over 4 log z, as long as z is sufficiently large, just at least 16. Okay, so what that tells us in our case is that the number of good b is at least s divided by 4 log s. Okay, so so good b's are relatively prevalent. Okay. Okay, so now the next thing that we're going to show is about the probability of measuring a good b. So for this, we're going to fix a good b, okay? And we claim that the probability that we see this good b when we measure the Fourier transform of gt is at least 1 over 25s, okay? So this is independent of t, right? So this holds for any gt. Okay, so if the probability of seeing any fixed good b is at least 1 over 25s, and we know that the number of good b's is at least s over 4 log s, then that means that overall the probability of seeing a good b is at least 1 over 100 log s. Again, that's the lemma that we wanted to show. Okay, so now it suffices just to show this claim. Okay, so we fix a good b. What is the probability that we see that good b when we measure the Fourier transform of gt? Okay, good. Now for this claim, the important thing is that there's an integer k such that b times s is close to k times n. Okay, we no longer, for this claim, it's not important that k is relatively prime to s. Okay, so this is the only fact that we're going to use about b for this claim. Okay, good. So, the first thing that we have to do, and this is where it gets slightly technical, is we just have to compute the amplitude of the bth entry of the Fourier transform of gt. Okay. Okay, so what is that? Well, we just have our normalization here. And then we're going to have the sum over y mod s equals t, right? Those are the states. So gt is just the sum over y mod s equals t of ket y with normalization. Okay, so when we look at the bth entry of the Fourier transform, what we're going to get is the sum over y mod s equal to t of omega to the minus b times y. Okay, now I'm just going to rewrite y mod s is equal to t, so that means that y is of the form j times s plus t. So I'm just written that here. And now I've factored out the factor of omega to the minus bt. So now we just have this sum. And then this is just a geometric sum. So this is going to be equal to this, right? So if omega to the minus bs is equal 1, then this sum here is just going to equal LT. Okay, so then the sum becomes this. Otherwise, we can use the formula for a geometric sum, and we get that the sum is this. Okay, right. So geometric sum with factor omega to the minus bs, yeah, gives you this part here. Okay, so that is the amplitude on the bth entry. So we're interested in the magnitude squared of that. Okay. Okay, and we're going to focus on this case where omega to the minus bs is not equal to 1. Okay, so I mean, there's nothing to do in this case. That's already computed here. Yeah. Okay, so this is what we computed from the last slide, and we want to compute the magnitude of the squared. So you see that both in the numerator and the denominator, we have terms of the form 1 minus omega to the minus q for some number q. So let's just, in general, compute what is the magnitude squared of that. So the magnitude squared is going to be that times its conjugate. So I've just taken the conjugate here. Then you multiply that out, and you get 2 minus omega to the minus q minus omega to the q. Now this sum, omega to the minus q plus omega to the q, that's just twice the real part of omega to the q. So that's just twice cosine 2 pi q over n. And you also have a 2 here, so I've just factored out the 2. Okay, now we're going to use this half angle formula here. 1 minus cosine theta is equal to 2 sine squared theta over 2. And plug that in. So overall, we get that the magnitude squared of 1 minus omega to the minus q is quantity 2 sine pi q over n squared. Okay, so we just apply that formula. So we apply this formula here to both the numerator, this term, and the denominator. And we get that the magnitude squared of the bth entry is this. Okay, so the omega to the minus bt goes away, this squares, so we have NLT in the denominator, and then we have these sine squared terms. Okay, good. So some things to note that the dependence on t, so there is a dependence on t, but it's relatively minor. Remember that LT is either the floor of n over s or the floor of n over s plus 1. So that doesn't really make too big of a difference here or here. So remember before in the simple period finding case, this magnitude is only non-zero when b was a multiple of n over s. But now we have this, more gradual dependence because of the sine squared functions. Okay, so we're also going to get a non-zero probability of seeing things further away from a multiple of n over s. But what we want to show is that if b is close to kn over s, that we have a pretty good chance of so this magnitude is relatively large. Okay. Okay, so we basically just need to bound this term here when b times s is close to k times n. Okay, good. So let's say that b times s is close to k times n. So let's say that b times s is equal to k times n plus d, where d is between negative s over 2 and s over 2. Okay. So both the numerator and denominator, there's a term of b. So let's just look at the denominator, I guess. So that's sine of pi b s over n, and we plug in our expression for b times s. So that's sine of pi times quantity k n plus d divided by n. But now this additive pi times kn term, that's not going to matter for the magnitude of the sine function, right? So this is just going to be equal to the sine of pi d over n. Okay, so we can apply that reasoning to both the numerator and the denominator, just to simplify our expression a little bit. So we have that this is actually equal just to sine squared pi d lt over n divided by sine squared pi d over n And then we have our normalization term out here, the 1 over n LT. Okay, so now what we need to do is just to lower bound this ratio of the sine squareds. Okay, so what we want to do is show that as long as theta is not too large, so we want to bound theta away from pi over L. So as long as theta, is bounded away, bigger than 0 and bounded away from pi over L, then we can actually lower bound this term. Okay. Okay, so this I'm going to just do kind of a picture kind of proof. Okay, so here's a plot of, let's see, it's 5 there. So I think there's a sine of 5x divided by sine x. Okay, so you see what it looks like. So this must be pi over 5 there. Okay, so the point here is just that this ratio of sines, as theta goes to 0 by L'Hopital's rule, you can see that is L. But when theta is pi over L, then the numerator is will just be 0, right? So that becomes 0. Okay, so we have something which is large at 0. At 0, it's L. At pi over L, it's 0, and it's a decreasing function on that interval. Okay. So if we look at the interval between 0 and something bounded away from pi over L, like something like 3/4 times pi over L, this function, is going to be minimized over that interval at the right endpoint. So at 3 pi over 4L. Okay. So in the picture, 3/4 pi over L is whatever, maybe it's something like here. And you see that on this interval, that's where the function is minimized. Okay, so we can lower bound this function over this interval just by plugging in theta equals 3 pi over 4L. So that's what I've done here. And, let's see, I guess we have to use something here, right? So I'm just using to upper bound the denominator, I'm just using the fact that sine x is at most x, okay? So this is just a little computation to get this lower bound of √2 over 2 times 4L over 3 pi. Okay, so now we have a lower bound on that. And what we just need to show is that our argument here, right, this pi d LT over n, it actually is bounded away from pi over L, right? So we want to show that is like at most 3 pi over 4, 3 pi over 4L. Okay, so okay, so what is this? So this is like, so LT is at most n over s plus 1, right? Because it's at most the floor of n over s plus 1. And then D is at most s over 2. Okay, so just plugging that in, we get that this is pi over 2 plus pi over s over 2n. Okay, and s is at most n over 2. So this will be at most 3 pi over 4. Okay. Right. Okay. Super. Right. So we bounded this away from pi, right? Because the numerator becomes 0, when this argument is pi. Okay. Good. So now we can apply the bound from the previous slide, and that tells us that this magnitude squared is at least 8 over 9 pi squared times LT over n. And again, if you just know that LT is going to be at least like n over 2s, just as a rough bound. So plug that in and simplify, and that gives you that this magnitude squared is at least 1 over 25s. Okay, so this proves the claim, and then that also finishes the proof of the lemma. Okay, so now you actually have all the gory details of the proof of correctness of Shor's algorithm for this relaxed period finding problem.